All right, we are on chapter 2, section 6, and we're talking radiation units and half-lives. Second to last section, we got this. All right, so radioactive units. So the amount of radioactivity present in any given isotope is counted as the number of emissions of those radioactive particles being emitted, or they call those disintegrations that occur in a second. So how many particles are being given off per second? And so the measuring unit that we use for that is the Curie, and that's named after Marie Curie, who studied radioactivity, right, with Henry Becquerel. I can always say his name right? So there's another unit for measuring disintegrations after Becquerel, and that's BQ for Henry Becquerel. So either one is measuring the same thing, but they're different units. And so when we talk about, oh, this isotope is very active, radioactively active, and this isotope is not, it's talking about how quickly or how slowly it's emitting radiation, right? So the more activity, the faster it emits all that radiation and the more dangerous it can be. So our relationship, the Becquerel is one disintegration per second. The Curie is 3.7 times 10 to the 10th disintegrations per second. So this, if you get one Curie of radiation, that's super dangerous. So a lot of times they use the millicurie or the microcurie. So every radioactive isotope emits radiation at a different rate. They're not all equal. So the more unstable an isotope is, the faster it emits radiation. And so we measure that rate of decay as the half-life. So the time it takes 1/2 of the atoms in any given sample to decay. And we call this the physical half-life. And that's like if it's sitting out in the environment, you don't do anything to it, you just wait, and that's the time it takes half of the atoms to decay. Now, if you put that radioactive sample inside of the body, not only do you have that physical half-life, but also you have a biological half-life. So maybe you're going to urinate a bunch of it out and get rid of it. You're going to eliminate it from your body that way. So you have to take into account both the physical half-life and the biological half-life for medical isotopes. So if you can combine those two, the physical and the biological, we call that the effective half-life. So what is it really inside of a person? And so we measure that decay with a Geiger counter. It's a little thing that kind of beeps at you when you have more radiation. You don't want it to beep too fast because that's a bad thing. So most natural radioisotopes have a really long half-life. One you can see here is carbon-14. Carbon-14 is what we use to date rocks and fossils and things like that. And so we abbreviate that, right, carbon-14, and it has a half-life of 5,730 years. So it takes a very long time. That is not what you want for radioisotopes that are used in medicine. You want medical radioisotopes to have a very short half-life, and you want that radioactivity out of the person's body quickly so that it doesn't build up and doesn't give them cancer, right? You're trying to treat them, not harm them. So if you look at some examples of radioisotopes that are used in medicine, what you're going to see is that column for effective half-life is much, much, much smaller. So here we're looking at years, even billions of years, where here we're looking at days, minutes, hours, something like that. Here's one we were talking about in one of the last lectures, Tectanium-99. This is one that's very commonly used, and it has an effective half-life of 4.8 hours. So in less than 5 hours, you have half of what you originally started out with. That's the half-life. So what do you do to determine the half-life? We're going to do some examples of this, but you want to determine the total number of half-lives that are passing in whatever given time. Like if somebody asks you in 30 hours, how much of this is left? Well, 30 hours is how many half-lives? You have to figure that out first. Then you can determine the amount of isotope remaining. And there's an equation that you can use, and it tells you the amount of the isotope remaining is equal to the half-life, 1/2, and another way to write 1/2 is 0.5 raised to the n times however much you started out with. So whatever you start with. So whatever you end with is equal to the half-life raised to however many half-lives there are times the starting amount. So let's go and do some of these. So, oh yeah, we got a little vocabulary first. What is the unit millirem measure? Millirem, and you have two, millirem and the sievert. Both of those two are going to measure clinical damage, biological damage, right? Specifically, the millirem is going to look at the amount, right? Amount of radiation per kilogram of the body mass, right? And so the larger the person, the more radiation they can take. A small child cannot take a lot of radiation. What does the unit Curie measure? Curie measures disintegrations per second, right? Disintegrations per second. Okay, so let's talk about some half-life stuff. How do the radioisotopes used in medical imaging differ from naturally occurring? Remember we said naturally occurring, it's going to take a long time for a half-life to happen. In medical, right, we want to have short half-lives. Very, very short. These are the ones that they're usually created in the lab. Not always, but a lot of times they're the ones that are created in lab. And we design them that way. All right, let's see. 2.37, a brain scan uses the radioisotope hydrogen-15. The recommended dosage is 50 millicuries. A supply of 250 millicuries and 20 milliliters arrives at the lab. How many milliliters will be injected into the patient? So start out with what you know and what you don't know. So we have a recommended dosage of 50 millicuries, and we're given a supply in a certain concentration. And now we want to know how many milliliters are going to be injected, that's my end, into the patient. So I'm starting with 50 millicuries, and this is just one of those dimensional analysis problems, right? So we want millicuries on the bottom so that our units will cancel, and we're trying to get to milliliters. And that's what we want our answer to be, in milliliters. So our millicuries will cancel. So what does the problem say? It says 250 millicuries in 20 milliliters. So do 50 times 20 divided by 250 gives you 4 milliliters. And yes, one significant figure. I hate that one. There's only one significant figure. Okay. The next one, radioactive indium-111 has an effective half-life of 2.5 days. If a dose with an activity of 3 millicuries is injected in a patient to detect blood clots, how much of the indium-111 will be active 10 days after the injection is given? Okay, so first of all, what we need to know is how many half-lives is 10 days? Right? We're given a day, but what is that in half-life? So remember, the first thing was to determine number of half-lives. So number of half-lives. Okay, so that's the first step. So how do we do that? We say 10 days. Well, there's a conversion factor that's in here. We were told that one half-life is 2.5 days. Right? So our days will cancel and we'll end up with what we want, half-lives. So that's 4 half-lives. Now I'm going to show you the second step. I'm going to show you 2 different ways. I'm going to do it stepwise, and then I'm going to show you the formula. Okay? I'll show you it's kind of the hard way, but it explains things. So if you're going to start out with 3 millicuries, right? And I need to go 4 half-lives to figure out what's going on. So my first one this is going to be 1 half-life, and that's going to be 2.5 days, right? So in 1 half-life, I'm going to get half. So if I take 3 divided by 2, I'm going to get 1.5 millicuries. But that's only 1 half-life. I figured out I have to go 4 half-lives. So I got to do it again. So this is my second half-life. And at this point, I've gone about 5 days. So after 5 days, I have to take that 1.5 and divide by 2. I get 0.75 millicuries. But I've only gone 2 half-lives, so I got to do it again. So this is going to be my third half-life. And this is about 7.5 days. So I'm going to take 0.75, I'm going to divide by 2, because that's what a half-life is. The amount of time it takes half of the material to decay. So 0.75 divided by 2, 0.375 millicuries. But I've only done 3 half-lives, so I need 1 more. So here we're doing this is our 4th half-life. After our 4th half-life, we've gone 10 days. That's what we were looking for, our 10 days. And so 0.375 divided by 2, we get 0.19 millicuries. You can do that. That's fine. I'm going to show you a second way to do it. You can use the formula that was in the textbook, right? And our formula in the textbook says whatever we have left is equal to a half-life. I'm sorry, 1/2 raised to the half-life. And so we're doing 4 half-lives, so we're going to raise it to the 4. And then we're going to multiply by our starting amount. Okay, so I'm trying to figure out what was left. That's my unknown. 1/2 is the same thing as 0.5. Do 1 divided by 2 in your calculator, you get 0.5. So type in 0.5 and then do the little caret. It looks like, the little caret looks like that. So you would have in your calculator 0.5 and it would be a little caret, and then, know what I did. Okay, so it would be a little caret, and then you would put the 4. And so that's 0.5 raised to the 4. This is what you would put in your calculator, okay? So raised to the 4, so hit enter, and then you're gonna multiply by 3 millicuries. And so what's left should be equal to the same thing. I got 0.1875, and I'm gonna round that to 2 significant figures, so 0.19 millicuries. I get the same answer. Either way is fine. Either way is perfectly fine. Okay, that's it.